Hello my dear students, I welcome you to Neet World. So today we will be discussing about hyperconjugation. So in the last class we have discussed about inductive effect and its applications. Then next we have discussed about mesomeric effect and its application, and today we will be discussing about hyperconjugation. So these three are permanent effects, and these three, if you are clear with these three effects, so we can solve most of the questions from organic chemistry. So even without knowing the exact name of some chemical reactions, we can able to tackle those questions using these concepts. So I will show you those kind of questions also in the upcoming sessions. So as of now, let us have some clear idea on this hyperconjugation. So once after doing this, we will be discussing some application based questions from this topic also. Okay, so what exactly hyperconjugation here? Okay, here just look here. So it is a delocalization of sigma electrons. It is a delocalization of alpha CH sigma electrons with the vacant p orbital or the anti-bonding pi orbital of something like alkenes. For example, here let us say I have a carbocation. So we know carbocations are electron deficient, and these are the reactive intermediates in chemical reactions they may form, right? Okay, so now let us say this is the carbocation I have given. So how this carbocation is stabilized by this hyperconjugation we will be seeing here. See, this is a carbocation, which means it is an electron deficient site. Now this carbon requires some electrons to stabilize this, right? Okay, so now how that will be stabilized here? So just check here, we know carbocation, which means here I can write like this. See, I just wanted to write in this expansion form like this. Okay, now around the carbon we know there are only 6 electrons here. Around the carbon we have only 6 electrons. 1, 2, 3, 4, 5, 6 electrons are there. So we have an empty p orbital like this. Empty p orbital we have. Now here just look here, the carbon which is adjacent to this is a carbon, which is carbocation. The adjacent carbon is called alpha carbon. So on this alpha carbon we have 2 hydrogen atoms. Okay, so what is this carbon? Alpha carbon. And the one which is adjacent to this will be beta carbon. So in the definition we have mentioned alpha CH sigma electrons will delocalize into the p empty orbital or vacant p orbital. See, on the carbon we have this is empty p orbital. So into this empty p orbital, this sigma CH electrons will be delocalized. Like that, the carbocation get stabilized. See here, how many electrons are there previously? 6 electrons are there in this carbocation. It means it required 2 more electrons to fulfill its octet. So that 2 electrons are coming into this carbon orbital by delocalization of this sigma bonded electrons. So this is how this carbocation getting stabilized. Like that, how many conjugations are possible? So we can delocalize the sigma electrons from this CH, from this carbon and hydrogen, which let us indicate with A, and this one CB hydrogen also. So it can have 2 delocalization structures or resonating structures. I will show you in detail here. So let us take ethyl carbocation. So here I am writing CH2 plus, so which is attached with the methyl group like this. Okay, now to this carbon this will be the alpha position, and alpha carbon and the hydrogens which are present on the alpha carbon are called alpha hydrogens. So the delocalization of alpha CH sigma bonds, how many alpha CH sigma bonds are there? 3. Okay, so each time one of these sigma bond can delocalize into this empty p orbital of this carbocation. Like that, how many we have? 3 sigma bonds. So 3 resonating structure or 3 hyperconjugative structures are possible for this carbocation. Okay, so more the number of resonating forms or more the number of hyperconjugative forms, more is the stability of that particular carbocation. So how this will be stabilizing here? So if you look here, this sigma bond electrons can shift into this empty p orbital like this, and we can get a structure like this. See, there is a disconnection of this sigma bond between carbon and hydrogen, and this will be shifting into this vacant p orbital of the carbon, and we are getting a carbon carbon pi bond, and here hydrogen remains with some positive charge. Okay, so you should remember that this hydrogen will not go anywhere. This will be firmly or like it will be connected, or it will be bonded, or it will be attracted by this pi electron cloud, so it will be remains here only. Okay, like that, this is a one carbocation possible, one resonating structure possible. And similarly, let us say this is HCA. Similarly, we can do with this HB hydrogen also, and with HC hydrogen also. I mean, just to differentiate how many hydrogens are there, so I have taken HA, HB, HC. So this is first resonating structure we can get, and second resonating structure we can also get when we are shifting this instead of this. So by shifting this bond instead of this, we can shift this one like this, so that we can get like this, no? So I hope this is also clear. So this is the second resonating structure. So this is HB. So this resonating structure came by delocalization of this CH, that is CHB, like carbon B, which is mentioned as B, hydrogen B, which is mentioned B here, to differentiate them. Now similarly, we can get one more resonating structure when we can delocalize this C and hydrogen, which is mentioned as C. So because three hydrogens are there, so three of them can participate in the delocalization. Therefore, we can get one more resonating structure. So that will be like this. This is HA, HB. Now HC is donating its sigma bonded electrons. Like this, we can get three hyperconjugative forms. So like this, so more the number of resonating structures, more will be the stability of that particular carbocation. So what I am writing, see how many alpha hydrogens are there on these. So 3 alpha hydrogens are there. Therefore, how many delocalizations are getting here, how many hyperconjugative structures are having here, these are also 3. So I can write number of alpha CH sigma bonds, number of alpha CH sigma bonds equals to number of number of resonating structures will be equals to number of alpha CH sigma bonds. So here how many delocalization forms are getting? 3. So I can write number of hyperconjugative forms. Number of hyperconjugative forms equals to number of alpha CH sigma bonds. So this statement is important here. So how many resonating structures or hyperconjugative structures are getting? So that will be equals to number of alpha hydrogen in that particular species, that particular carbocation or free radical also. Okay. So this is one application here. So I just want to confirm from you whether are you able to identify alpha hydrogen or not. So here I just wanted to give this carbocation. Okay. It is having this side CH3 and this side CH2 and this side CH3. So tell me how many alpha hydrogens are there in this carbocation. So how to identify? This is the carbocation site. To this, the adjacent carbons are called alpha carbons. So it means this is alpha carbon, this is also alpha carbon, and the one which is next to alpha carbon can be called as beta one. Okay, beta carbon, right? Okay, if another one is there, that should be gamma. Like that we have to give the naming for them. So now what I told you, in the hyperconjugation only alpha CH sigma bonds will be involving, right? So here this is alpha carbon, this is also alpha carbon, and the hydrogens attached to this alpha carbon are called as alpha hydrogen. What is that? Alpha hydrogen. So how many alpha hydrogens are there? Here it is 2, here it is 3. So total 5 alpha CH sigma bonds are present. So total 5 alpha CH sigma bonds are present. Therefore 5 resonating structures are possible. How many resonating structures are possible? 5 resonating structures are possible for this particular molecule or this particular carbocation. I hope this is clear. Okay. So now what I told you, so we can say here the condition for hyperconjugation is what? At least one alpha CH sigma bond should be present. Okay. So I just want to show this the orbital representation also for this. See here we have ethyl, whatever the example we have discussed previously. So that is what the same orbital representation. Just look here. So this is the carbon with positive charge. I can say carbocation, which is electron deficient. So let us indicate the empty orbital of this carbocation like this. Okay. Now here we have 3 hydrogen atoms like this. Now, okay. So this is the s orbital of hydrogen. This is a p orbital of carbon. Therefore, they are having this electrons which we are representing them as which we are representing them with this what? The bond, sigma bond. So now this sigma bonded electrons, these sigma bonded electrons will be shifting over here. See, this is how the sigma bonded electron cloud is shifting here, and it is stabilizing this carbocation. So see, this is the sigma bond of carbon and hydrogen shifting into the empty 2p orbital of this carbon. Therefore, its valency getting satisfied for this carbocation by filling its octet configuration. That's how the carbocation stability takes place. I hope this is clear. Okay. Next, let us see what is the condition. I told you at least one alpha hydrogen should be attached. For example, see, alpha hydrogen, if it is attached to alkene, so alkenes get stabilized by hyperconjugation. I will show you example. Even for if it is attached with benzene ring also, any alpha hydrogens, it means any alpha CH bonds are present on benzene, so that alkyl benzenes also getting stabilized. I will show you the example also. Okay. Then next, even for carbocation, I have discussed already, if there is any alpha hydrogen, that can be also stabilizes this carbocation. Similarly for free radical, we will be discussing them one by one now. Here, the next here is what are the applications we have. So what are the applications? Stability of carbocation we can explain using the hyperconjugation, and stability of free radical we can explain, and then next stability of alkenes we can explain, the next stability of alkyl benzenes and bond length in them. So these are the applications we have from hyperconjugation. Let us discuss one by one from these applications. Okay. So here let us discuss let us start our discussion with carbocations first, then next free radicals. So write this heading, applications of hyperconjugation. In the first heading is stability of carbocations. Let us say I have these are the 3 carbocations, methyl carbocation and the next ethyl carbocation like this. Okay. So like this, let us increase the alkyl sign, and I have CH3 CH CH3 like this, and the next one more let us take CH3 C CH3 CH3, and the next CH3 here also, and positive charge. So these are the different carbocations we have. So tell me, so I told you in the when we are studying about carbocation intermediates, so how can we name them? So if any carbon is directly attached to the carbocation site, this carbon is carbocation site na? To this, if any carbon is directly attached, so if it is one carbon attached, we can say primary. Okay. If 2 carbons are attached, we should say secondary. What is that? Secondary. So here 2 carbons are attached na? So we should say secondary carbocation. This is primary carbocation. And here how many attached to this like carbocation site? It is attached with 3 carbons directly. So I can say this is tertiary carbocation. So these are the classifications. Now out of these 3, which carbocation is more stable, they may ask. So how can we answer this kind of questions? I told you, if any alpha carbon is present and on alpha carbon any alpha CH bonds are present, any alpha CH, see this is alpha carbon, and these hydrogens we can write them as like this now, like this now. So this CH alpha CH sigma bonds can be donated into this empty orbital of these carbocations. That's how it can be stabilized. So now for this secondary carbocation, how many hyperconjugative structures are possible? So what I told you, just you need to identify number of alpha CH sigma bonds. How many are there? If this is alpha carbon, the hydrogen will be alpha hydrogen. So like that we have 1, 2, 3 alpha hydrogens are there this side. Similarly, we have this side also. So total how many? So 6 CH alpha sigma CH bonds are present. Therefore 6 hyperconjugative structures are possible for this. Similarly here how many are there? This is alpha, this is also alpha, this is also alpha. So that we can get 9 hyperconjugative structures for this. And what about this? Here it is having, this is alpha for this carbocation, this is the alpha position. No? So we have 3 alpha CH sigma bonds are there. Therefore it can be stabilized by 3 hyperconjugative structures, right? And there is no hyperconjugation in this case. So more, what I told you, more the number of hyperconjugative structures or more the number of resonances, more is the stability. So it means this carbocation is more stabilized by 9 hyperconjugations. Therefore which is more stable carbocation here? Tertiary carbocation is more stable than the secondary, then next primary, and least is methyl carbocation. Like this we need to answer the question. I hope this is clear, like application of hyperconjugation with respect to carbocations. Let us discuss 1 or 2 questions more. So I just want to mention a cyclopentane having a positive charge over here, and the next like this, okay, that is also positive charge. Now one more I want to take here is so tell me, out of this ABC, which carbocation is more stable? So how can we answer this kind of questions? Tell me fast. Okay, so first of all you can directly find this whatever the application we did here, you can just go with that. See, first of all identify them, what is the degree of those carbons which is having positive charge. So this is 2 degree carbocation, this is 2 degree carbocation, and what about this? To this carbon which we need to stabilize, that is 3 degree carbon. How I am giving it is 3 degree? Because this is directly attached to here also carbon, here also, and here also methyl. So we can say this is 3 degree carbocation, tertiary carbocation. What about this? This is also 3 degree carbocation. Now all of them are like these 2 are 3 degree. Now what we need to check, in order to stabilize this carbocation, we have to check number of alpha hydrogens attached to it. So how many alpha hydrogens are there for this carbocation? See, this is the alpha carbon, this is also alpha carbon with respect to this carbocation. Similarly this is also alpha carbon, this is also alpha carbon, and this is also alpha carbon. Okay, now for this, here we have alpha, here alpha, and here also alpha. So on each alpha hydrogen, just check how many hydrogens are there. So here 4 alpha hydrogens are there, here 2 and here 2. 4 alpha CH sigma bonds are there, therefore 4 hyperconjugations are possible for this A. And here also we have hydrogen, 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 hydrogen. So 2, 4 and here 3. So 7 alpha hydrogens are there, 7 hyperconjugations are possible for in case of B. Now for C, 1, 2, here also 3, 4 and here 2. So here in this case, in option C, there are 6 alpha hydrogens, or 6 hyperconjugations are possible. So tell me, in which case more hyperconjugations are possible? In case of B. Therefore B is more stable than C, because 6 alpha hydrogens are there, 6 hyperconjugation, then EA. So this is how we need to answer the stability of carbocations. I hope this is very clear. If you have any doubts, let me know in the comment box. Okay, so I just want to give a homework question for you. So just tell me the answer for this. So take the question number 1 and write this as a homework. So tell me answer in the comment box. Positive charge, positive charge. A very simple question it is, and positive charge. So this is consider A, B, C. So tell me which is more stable, which is least stable. Write the order of the stability of these carbocations, and in the comment box we will discuss there if you have any doubts on this. Okay. The next thing is, let us discuss about stability of free radicals. What I am discussing now? Stability of free radicals, let us discuss. Okay. So write the heading as stability of free radicals first. Stability of free radicals. So it is also similar to carbocation stability only. So let us say here I have free radical carbon which is attached with the methyl group. So this is ethyl free radical, can we say this is ethyl free radical? Yes. Now here it is having one electron, one odd electron, and around this carbon, free radical carbon, just count total number of electrons present. So like this we are writing now. So 1, 2, 3, 4, 5, 6 electrons are there, and this is the odd electron which is present here. So totally 7 electrons are there in this free radical. Okay, so we can say free radicals are paramagnetic in nature. What is it? Paramagnetic in nature. Okay, now here I can shift one of these electron from this alpha carbon carbon hydrogen bond. See, this is the alpha carbon now. So this electron, one of this electron to pair up with this free radical electron, therefore they will get octet configuration, 8 electron configuration, and become stable. See, now I am shifting this sigma electron from here to here like this, and it is pairing up with this, therefore we will be getting a resonating structure or hyperconjugative form like this. See, carbon, I am writing these bonds as it is, next this is side carbon, and which is having 2 hydrogen atoms, here one, and see this electron and these electrons are getting paired up here. So let us indicate with some different color, and here one hydrogen is there. So hydrogen electrons is staying with this hydrogen itself. So this is how the hyperconjugative structure we got from first hydrogen, alpha hydrogen. Like let us say this is A hydrogen, this is B, this is C, something like this. So we have drawn the structure with respect to alpha CH, which is A hydrogen. Similarly we can get with B and C also. Like that, number of alpha hydrogens gives that many number of hyperconjugative forms. So here how many hyperconjugative forms we can expect? So here it is 3 alpha hydrogens, therefore 3 hyperconjugative structures we can get for this free radical also. So it is the story similar to carbocation only here also. Okay. So now tell me, out of these 3, so as discussed above, I just want to mention the same free radicals. So this is the secondary free radical, this is a tertiary free radical. Tell me, out of these 2, which free radical is more stable? And if you want, let us add one more free radical also. Let us make it primary. Primary free radical. Tell me, out of these 3, which free radical is more stable? So if you want, let us make it more interesting by adding some other groups. Yeah, tell me, out of these 3 structures, which is more stable? A, B, C. Which free radical is more stable? Yeah, so this has to be stabilized by alpha hydrogens. So how many alpha hydrogens are there? To this carbon, this is a alpha carbon, right? An alpha carbon, we have one hydrogen. So it means only one alpha hydrogen is there. It can be stabilized only one time. So I can say one hyperconjugation is possible in this case. How many hyperconjugations are possible? That will be equals to number of alpha hydrogens. So that is only one alpha hydrogen. So we can get only one hyperconjugative structure. Okay. Similar to that. So what about in the second case? So for this free radical we need to stabilize. For that we have 2 alpha hydrogens this side, and similarly this is alpha carbon, here also we have 2 alpha hydrogen. Therefore we can get 4 hyperconjugative structures for this. In this case, see, this is a methyl group, it means here we have 3, and what about here? We have here 2, and here also 2 alpha hydrogens. Therefore we can get 3 plus 4, 7 hyperconjugations are possible. Therefore I can write the answer as C greater than, C is more stabilized, then B, then A. So this is how you need to answer the questions from carbocations and free radicals. I hope this is very clear. So let us look for the stability of alkenes. So what is the third application we have? Stability of alkenes. So alkenes are stabilized by hyperconjugation. Let us say here I have like this I have. For this, let us add one methyl group. Let us attach one methyl group for understanding purpose. See, this methyl group is attached to this alkene. Okay, now this is a alkene functional group we have. We need to stabilize this alkene functional group. So for that, the adjacent carbon is called alpha carbon and the hydrogens present are alpha hydrogens. We know this story. So now how many alpha hydrogens are attached to this alkene are 3. So 3 alpha hydrogens are attached. Therefore this alkene is stabilized by 3 hyperconjugative forms. So I will show you how these 3 alpha hydrogens stabilizes. So let us write them with clearly representing them like this. Now just see here, this is the pi bond now. In the definition we have written the delocalization of alpha CH sigma bond with the pi star orbitals of alkenes. It means this is the pi bond now. So for pi bond there will be respect to pi star orbital will be there. Okay, so into that orbital, so these electrons will be delocalized or shifted. Therefore when it is shifting here, so this bond will be shifting onto this carbon and we will be having a negative charge on the last carbon, terminal carbon, like this I will be representing here. CH. Here bond is disconnected, therefore I am representing them with positive charge. Here between this carbon and this carbon we are getting a pi bond, a new pi bond. So I am writing that new pi bond, and when it is forming a new pi bond, so this pi bond is disconnected, right? So it means I can write this pi bond as a negative charge on this carbon. So like this, how many resonating forms we can get for this structure? There are 3 alpha hydrogens we can get. When I am shifting A hydrogen, we will be getting like this structure. When we can shift B, then also we can get a hyperconjugative form, and if it is C, so we can get with respect to this alpha hydrogen also. Therefore 3 alpha hydrogens are there. So 3 hyperconjugative structures are possible for this alkene. So more the number of alpha hydrogens attached to the alkene carbons, more is the stability of that particular alkene. So I will show you one example here. So take this as a question. So we have like this. Like this, and the next example like this we have. So tell me, out of these 3 alkenes, which is more stabilized? Which is more stable alkene? So this kind of questions we may get in the exam. So out of this ABC, which alkene is more stabilized? So tell me fast. So I can go that option C is more stabilized because it is having how many alpha hydrogen? Just check. So this, if this is the carbon-carbon alkene double bond functional group, so to this functional group carbon, how many are attached here? This is the alpha carbon, I can say 3 alpha hydrogens are there here, and similarly this side also 3 alpha hydrogens are there. Therefore 6 hyperconjugations are possible for option C. In case of option B, see here how many alpha hydrogens are there, just find them first. So identifying alpha carbon and identifying alpha hydrogens are very important and crucial thing in order to understand the hyperconjugative structures. So tell me, to this alkene, the adjacent carbon is called as alpha carbon and hydrogens are alpha hydrogen. Therefore I can say 3 hyperconjugative structures are possible for this B molecule, right? And what about this? No alpha hydrogens are attached to alkene. It means no hyperconjugation in this structure, right? I hope clarity, like explanation is clear. Now based on this explanation you can answer directly. So tell me where the hyperconjugations are more? In C. Therefore option C is more stabilized than B then least is A. So this is how you need to arrange based on their like stability. Now I also told you in the last applications, first I written applications of hyperconjugation. First thing is stability of carbocation, next carbon and free radical I told you, then next stability of alkenes I told you, then next alkyl benzenes, and the least I have written it as bond length. So what is the application of bond length here? I just want to mention here itself. Okay, so which out of these three, which bond length is more? Let us say this double bond is there now. So for that let us take here for more better understanding. Here the bond length here, double bond is there now. Let us indicate this with bond length like bond as A bond, and here I just wanted to mention it as CH2 double bond CH CH3, and this double bond this pi bond as this alkene group bond as B. Tell me, out of this A and B, which bond length is more? Both are alkene functional groups only, but I am asking arrange them based on their bond length order. So how can we answer this kind of questions? See, here we know in first case in CH2 there is no hyperconjugation, so it means there is no disturbance for this double bond. But here hyperconjugations are there now. So how we get hyperconjugation? So from this alpha carbon to this functional group, this is alpha carbon now. So by these alpha carbon hydrogens hyperconjugations are possible. Therefore this double bond become single bond, like by participating hyperconjugation, and become single bond, and the bond length increases. So just check here. So this double bond will be becoming single bond when these hyperconjugations are involved. Just check here. So here three are there now. So let us write them CH, CH, CH like this. So now when it is involving in the hyperconjugation like this, so this bond is shifting over here now. It means what happens here? So the resonating structure should be indicated in this manner. So when it is shifting here, the double bond becoming single bond now, therefore bond length what happens? Increases. So we know double like bond length is more for single bond, then next double bond, and the least is for triple bond. Therefore the double bond becoming single bond means bond length is getting increased for this B. So I can write this as CH2 negative charge, and when it is shifting here I can write CH2 like this and H plus. So this is how the hyperconjugation taking place, and multiple like pi bond become like double bond becoming single bond. I can say bond length is increased. So which like what is the order? B is greater than A. So this is the one more application from hyperconjugation, that is on bond length. I hope this is also clear. Okay. So I just wanted to give one question for you. Take this question as a question number 2, and let me know in the answer for this question in the comment box. Like see, option A is this is alkene, ethene you can say, and option B is this one, and option C is this one, and option D is like this, and option E is this. These are the options I wanted to mention, and arrange them based on the increasing order of the stability. Increasing order of stability. Which alkene is more stable? Which alkene is more stable? Like that, make the order of based on their stabilities, and like give your answer in the comment box. I hope this is also clear. The last application we have is stability of alkyl benzenes I mentioned. What is the stability of alkyl benzenes? Let us say. So write the heading as stability of alkyl benzene. Stability of alkyl benzene. So here just take some alkyl benzenes. See, this is benzene with the methyl group. So this is an example of alkyl benzene. So name of this compound is toluene, right? And the next thing is, we can say this is also benzene with ethyl group, so we can say ethyl benzene. The next we have propyl benzene here. So propyl benzene. So out of this A, B, C, which alkyl benzene is more stable? Which alkyl benzene is more stable? So how can we answer based on this hyperconjugation? Just consider here, instead of writing this as a like a resonating form, just write it with the double bonds like this. Now check, to this double bond alkene, can I consider this as alkene as an olefin? It's a double bond. To this carbons, this carbon is what? Alpha carbon. Na? It means these 3 alpha hydrogens can participate in hyperconjugation. So if it is participating in hyperconjugation, its stability increases, right? Therefore 3 alpha hydrogens in this case, so we can say it can give 3 hyperconjugative structures with respect to these 3 hydrogens. Similarly, here it is having 1 alpha, 1 beta carbon. We know only alpha hydrogens will involve, so it can give 2 hyperconjugative structures, right? Then next, here only 1 alpha hydrogen, therefore we can get 1 hyperconjugative structure in option C. So we know more the number of alpha hydrogens, more is its stability. So first case it is more stable than the second case, and least is C. So now I just wanted to show how this hyperconjugation taking place in this alkyl benzene for your clarity. Let us write it like this, methyl benzene. Now here this is a alpha carbon and alpha hydrogen, let us say A. So it can donate the electrons like this, sigma bonded electrons into the pi star orbital of this carbon, and this will be jumping into the ortho position of this phenyl group. Okay, right here like this. So this bond is getting disconnected and forming a converting into pi bond, and this negative charge should be represented here, and this pi bond, and hydrogen here as Ha plus. Like this hyperconjugation taking place with respect to this hydrogen and also this hydrogen and also with these hydrogens. So we can have 3 hyperconjugative forms for using these 3 alpha hydrogens. I hope this is very clear how we are writing hyperconjugations also, okay, in alkyl benzenes. Okay, so we can write other resonating structures also. I just want to mention how this alpha hydrogens of carbon is involving in hyperconjugation, that's why I have represented this. Okay, so you can make more resonating forms also. Okay, so in all these cases when we are drawing the structures, we have to observe one thing, that is there is no bond between carbon and hydrogen. Na? So the name of this concept, what is it, hyperconjugation, is also called as no bond resonance. What is that? No bond resonance, because this is an extension concept of resonance, and there is no bond between carbon and hydrogen during its stabilization. Therefore the name of this application, this concept is also called as no bond resonance. What is that? You can write the name as no bond resonance, and one more name, Baker-Nathan effect, Baker and Nathan effect. So these are the names given for this concept. Okay, hyperconjugation you may say, or you can say no bond resonance, or you can also call Baker and Nathan effect. Okay, so this is about the concept, and you can solve few more questions. Okay, so just give me answer for this question. So hyperconjugation involves overlap of what? So hyperconjugation involves overlap of following orbitals. Tell me which of the option is correct here. So pause the question, pause the video and answer, try to answer here. So here out of these 4 we discussed hyperconjugation involves delocalization of sigma CH electrons into the vacant p orbital. Yes. Otherwise sigma like sigma CH electrons into the pi star orbital of alkenes, right? These are the 2 things we discussed. Now check, is there any sigma like sigma to p orbital? Yes, here we have an option which is sigma and orbital p. And the next thing is, if I want to add one more option, option number 5 as sigma bond to pi star orbital. Yes, these are the 2 options you can choose when there is a question like this. Okay, I hope this is very clear. Okay, next thing is, yeah, so try to answer this, which alkyl benzene is more stabilized. Yes, similar question we have seen here. So 3 alpha hydrogens are there, so it can be stabilized 3 times. It means it is more stabilized. Here only 2 are there, so 2 times. It is having only one alpha hydrogen, so only one hyperconjugated form. No alpha hydrogen on this carbon, I mean like the one which is attached to benzene ring, phenyl ring, there is no alpha hydrogen on this carbon. This is the alpha carbon. On that carbon there is no hydrogen, so I can say no alpha hydrogen. So no hyperconjugation is possible in option C, option 4. Therefore, only 1, 2, 3 cases hyperconjugation is taking place, but out of that 3, which is more stabilized? Option 1, because more number of alpha hydrogens, more is the stability by hyperconjugation. So I can write the order as 1, 2, 3 and least is 4. So this is the order. So they haven't asked about the order, they just asking which is more stabilized. So I can say option 1. Okay, if they ask for order, you can go with this. Hope the concept is very clear. If you have any doubts, you can ask me. Okay, now tell me which free radical is more stable here. So we already discussed how the mesomeric effect also like plays when it comes to the stability of intermediates. So here see, pi bond is there, sigma bond and one radical. So we can expect here mesomeric effect also like this. Therefore we can get a structure, resonating structure like this, and a radical over here, radical over, yeah, so radical here, right? So this is what the resonating structure of this. So this is so I can say there is mesomeric effect in this radical stabilization factor. So what are the effects we can expect? So while doing the questions, while solving the questions, we need to check for the whether the given species is stabilized by mesomeric effect and also hyperconjugation and also inductive effect. These 3 effects we have to take into the consideration while answering a question. So here mesomeric effect is there, yes, plus m is there. Next, here we have 2 hydrogens which are on the alpha carbon. So I can say 2 hyperconjugative structures are also possible. Yes, it is stabilizing by mesomeric and also hyperconjugation. This is also clear. And this hydrogen won't involving in the conjugation with this, and as it is attached to the alkene carbon. Okay, so it means only these 2 will stabilize. And I can say this is as an alkyl group. If we consider this is as an alkyl group, so if we consider this is as an alkyl group, so I can say this is plus M effect is also present with respect to this alkyl group. Yes, so these are the plus I effect is also present with respect to alkyl group. So these are the 3 effects are there. So once again I just want to remind that if you are not aware of this, or if you are not clear with the mesomeric effect and inductive effect, go through my video lectures or the playlist given in the description box, or just go through the videos like playlist of this channel, and you can check for the general organic chemistry videos. That will be highly helpful for your preparation. Okay, then next here also we have same what like mesomeric effect is there as like here, and this is having more number of alpha hydrogen. Check, see, these are 3 and here 2, so 5 hyperconjugations are possible and 1 mesomeric effect is possible, and these 2 alkyl groups are there. So I can say 2 plus I groups are also possible. Okay, it is more stabilized than this, so I can say 2 is more stable than 1. Okay, now always remember, if on the phenyl group, on the phenyl ring, if any radical or any carbocation or any negative charge carbon anion kind is present, so those are highly unstable. So this is least stable. And here on the double bonded carbon also, if any radical or positive charge or any negative charge is present, we should call it as vinyl radical or vinyl carbocation or vinyl carbon anion. So these are also highly unstable. So which is more stable here we got? So option 2 is more stabilized. Okay, so this is the option you have to tick for this particular question. I hope the concept is very clear, and if you have any doubts regarding our discussions, so you can just let me know in the comment box. We will be discussing in the upcoming session. And guys, I just wanted to suggest you one more thing. So we have in the very few days we will be having NEET exam and EAP set for Telangana and AP students, right? So you just go through the previous year questions on this GOC part. Okay, so if you are having any difficulties while solving those questions, just tell me in the comment box. We will be discussing those questions in the upcoming session. So our next session is on aromaticity, and also one more session will be on the complete PYQs of this GOC part. I mean these 3 effects whatever we have studied. Okay, I hope the session is helpful for you, and if you really like our content, please give a like and share with your friends. So thank you for watching and happy learning.